Okay, let's continue our discussion. So in this video, we are going to uh, see how experimentally determine the value of universal gravitational constant. So here we have the setup, and the experiment was performed by Henry Cavendish. Yes, and in 1798. Yes, correct. So this is the setup. What is happening here? So one thing, this is rigid support, and this is fine wire, and this is a rod, and at the two ends of this rod is connected with two spheres. Let's say this is a sphere 1, and mass of these two spheres are indicated by a small m. So this is sphere 1 and this is sphere 2. Okay, now along with these two spheres there are bigger spheres placed opposite, and then due to these two spheres there will be gravitational pull, and due to that gravitational pull, as if they are at equal distance, let's say the distance between these two spheres is d, and of course the centers, we are taking the distance between the two centers here, so this is also d. So there will be equal and opposite gravitational force on this system, means the system which is in which there are two masses connected at the two ends of this rod, and let's say the length of this rod is L, or more precisely, the distance between the two centers of these two small spheres is L. Okay. So there will be gravitational pull, and this will be along this direction, and this will be along this direction. So gravitational pull, let's say this gravitational pull is Fg. So here we have Fg acting on the spheres. Now this gravitational pull and this gravitational pull both are equal in magnitude but opposite in direction. So if two forces which are equal in magnitude and opposite in direction, these two are going to give net force 0. So net force on the system is 0, but they are acting on different points, so there will be some torque. So let's say net torque. This is not going to be 0, and this torque will be, we have studied the concept of couple. So here this will be Fg into L, and L, look, why I have written directly, because this angle is 90 degree here also and here also. So FGL sine will be sine 90 will be 1, so I am writing directly here. So net torque will be this much. Okay, what will be happening here? If these two forces are acting, so there will be twist in this wire. So there will be twist in this wire, and to resist that twist, this wire will apply a restoring torque. So there will be a restoring torque. Let's say this is a restoring torque. The magnitude of this torque will be equal to the magnitude of net torque if this is in equilibrium. Means initially these two spheres are placed here. Let's say this is sphere 1 and this is sphere 2, and then there will be twist in the wire, and after some angle, let's say there is angle something here. So after some angle of twist, let's say these two spheres come to a rest point. So after twisting, it is coming to rest along this. Means the rod will be aligning this, and there will be two spheres at the end here. Okay. So if it is in equilibrium, it will be in equilibrium only when the net torque produced due to the gravitational pull and the restoring torque, these two should be equal in magnitude. Now, what about restoring torque? So restoring torque we can obtain. Look, we can experimentally obtain one thing here. This restoring torque will be proportional to the angle of twist. And if I'm just writing tau here and restoring, of course, I'm writing res here. So this will be something constant times theta. And this constant can be obtained experimentally by applying different values of theta here, by rotating this thing and checking what is the torque per unit angle here. So restoring torque per unit angle can be obtained experimentally here. Okay. So this will be restoring torque per unit angle times angle of twist here. And net torque due to gravitational pull will be Fg into L. Now we can further proceed here, and then we will have here K tau theta equals to Fg can be written as capital G, which is universal gravitational constant, and times mass of the bigger sphere times mass of the smaller sphere divided by distance square between their centers, and this is length of the rod. Now from here we can obtain what is the expression for G. So G will be K tau theta into d square divided by capital M times M divided by this thing M into N into L. Now we have all the values here. We have restoring torque per unit angle of twist, and then in this particular case what is the angle of twist here, and then we can yes, there will be distance, we can measure it, and then masses we have, and the length of this rod. So by putting these all things, one can arrive what is the value of G, and this is what Cavendish sir has done already. Now it was, the value was close to 6.67. I am writing here a refined value which was later obtained by several situations and experiments. So yes, here there will be unit, and I would like to say that you should write what is the SI unit of this capital G. You can extract this thing. Okay, in this way, capital G can be obtained. So this is the value of capital G. Now, coming to the next point. So in the previous video, we have studied the gravitational force due to a collection of particles, means gravitational force on a particle due to other particles. Now we are going to extend that thing, and we are going to study the gravitational force due to an extended body. And here we are taking a spherical bodies for time being. So gravitational force on a body due to hollow and solid spheres. So in first case, let's take this is a hollow sphere. Hollow sphere. So in case of hollow sphere, a body can be placed outside somewhere. Let's say there is a body here with mass m, and let's say in first case outside. Okay, mass m, and this is the center of this hollow sphere. So let's say this center is something C. Now this is the line joining the body to the center of the sphere, and if this distance is r, this distance is r, and mass of this hollow sphere is something capital M. So outside, the force, gravitational force will be Fg will be G M into N by R square. That is, this sphere is acting like a point mass at its center. Now, what about a body which is placed inside? Let's say here we have a body placed at distance d. Let's say this distance is d. Okay, or something arc like, let's say. So at this situation, when this particle or body is inside the sphere, the net gravitational force will be 0. And direction you can see here. It is radially inward towards the center of this. So we can write here along minus r cap. If we are taking, this is the direction, this is origin, and this is the direction of r cap, then this force will be along minus r cap. Okay. So this is outside, this is inside. Yes. At this point, I'm not going to give derivation or explanation how it came, but you can just qualitatively argue that for this body at this point, this sphere is going to be in two different regions. We can assume that there are two different regions, one here and look, one here and another region is here. And these two regions having mass, and these two masses are going to create equal and opposite gravitational pull on this body, and net will be, the resultant will be 0. So a detailed explanation you can get in further lecture videos when I will be starting for IIT Jam. Okay. Now what about solid sphere? So Let's move. Yes. In case of solid sphere, second case. Let's say here we have a body of mass small m, and here we have the mass of this sphere, capital M, and here we have center, and this is the line joining. So, okay. And now this distance is r, and let's say this is center. So, in the first case, when the body is outside the sphere, we can say the gravitational pull will be along this direction. Again, I am taking this direction to be r cap. So, a body outside the sphere, F g will be g m into m divided by r square, and along minus r cap. Okay, let me check whether I have given vector sign or not here. So here also, look, you have to be careful about these all things. So this is all. Now, what about for a body inside the sphere? Let's say we have a body here inside the sphere. So here we have a body and it has mass something m prime. Let's say m prime. And then this is the distance from the body to the center, and we can write this distance as r prime. Okay. So for this body, which is inside the solid sphere, look, we can assume a sphere of radius r prime here. And for that sphere, this body will be at its surface. And look, after extracting this sphere, we will have a shell outside. Yes, a spherical shell outside this sphere. And due to this spherical shell, as this body is lying inside the spherical shell, the net force, gravitational force will be zero. So the only gravitational force in this case, let's say Fg prime, the only gravitational force acting in this case will be due to this sphere, which has radius r prime. So we can write in the second case, when the body is inside the sphere, here we have f g prime, and this will be equal to g. And let's say the mass of this inner sphere is capital M prime. So the f g prime will be g m prime into small m prime divided by r prime square, and this is also acting along minus this. Okay, if we are taking this direction to be the direction of r, and look, direction of r cap and direction of r cap prime will be the same. So I guess no need to write this thing specifically here. So we can write only r cap. Okay, so this is in case of this thing. Now we have to check what is the mass in terms of this total mass of this body, this mass. So we can assume that this sphere is uniform. So if this sphere is uniform, then its density will be the same, whether we are taking the complete sphere or we are extracting apart from it. So in case of uniform sphere, the mass per unit volume will be the same. So m per unit v will be the m prime per unit v prime. Means mass of the sphere divided by volume of the sphere will be the mass of this inner sphere divided by volume of this inner sphere. And this is going to be mass density of this body, this sphere especially. So this is density. From here we can obtain that m prime is m v prime divided by v, and we know what is the volume of a sphere. So we can write this is mass of the sphere, complete sphere, and volume of the inner sphere will be 4 by 3 pi r prime cube divided by 4 by 3 pi r cube. And then we will have here m r prime cube divided by r cube. Okay, so we can replace n prime here with m, and then we will have f g will be F, G and S prime here. This will be, instead of M prime, we are going to write here M R prime cube divided by R cube and then M prime and into R prime square. And then we will have G M into M prime divided by R cube into R prime. This is what we are going to get in this case. Okay. Now moving to the next point. Now we are going to obtain acceleration due to gravity. So if this solid is here, let's say we are taking the case of Earth. So a body on the Earth or inside the Earth, there will be gravitational pull due to the Earth, and due to that gravitational pull, there will be acceleration. So that acceleration, we are saying acceleration due to gravity in case of Earth here. And we represent this acceleration due to gravity as small g. So let's take for a body which is outside the Earth. So here we have center, and let's say here we have a body here. So mass of this body is m, and its distance from the center of the Earth is, this distance is r. So what will be the gravitational pull on this body? This gravitational pull will be number one, outside. This gravitational pull, I'm writing F, G, and magnitude only because direction we can obtain. This is direction of r cap. So the force will be along minus r cap. So in this case, I'm taking magnitude only. So Fg will be capital G times mass of the Earth. Let's say Me is the mass of the Earth and its radius is r e. Capital E is here in subscript. So okay, here I am writing capital E in subscript. So Me and then mass of the body divided by r square, and then we will have G Me into M divided by this r is, we can write in two different terms. If we are taking its height from the surface as h, so the r will be re plus h, means from here to here is its radius, and then from here to here it is h. So r can be replaced with this value. So we can write gravitational pull F G, in this case outside, G Me into M and divided by Re plus H square. Okay. Now we can go for acceleration due to gravity. As we know that due to this gravitational pull, there will be acceleration due to gravity, and this acceleration due to gravity can be connected to this as mass times acceleration. So this is mass of the body and this is acceleration due to gravity, which will be equal to gravitational pull on the body, and then we can write G equals to Fg divided by mass of the body. So here we have to divide with m, which will eliminate this term. So acceleration due to gravity in this case will be, acceleration due to gravity in this case will be Fg divided by mass of the body, and it is going to be G me by Re plus h square. This is what. Now we can further simplify this scenario. So here we will have Gme, and we can take r square common. So here Re square common. Then we will have here, if we are taking Re square common, then we will have 1 plus h by Re here and the square of this thing. Okay. So we can write 1 plus h by Re to the power minus 2. And why I'm writing in this case, we can use binomial extension here. So we know that, and probably you have studied, I'm writing its simplest one. So 1 plus x to the power n can be written as 1 plus nx plus n into n minus 1 x square divided by 2 factorial plus n into n minus 1. Now you might have understood the pattern. N minus 2 divided by 3 factorial x cube. There is a general form of this thing also, but I am using the precise one which is needed here. So this will be in the same case. And if this x is less than 1, means the mod of this x is less than 1, then x square will be much less, and x cube. So we are going to, for in this case, we are going to neglect, means we can assume that the value will be sufficient up to here. So we can take 1 plus x to the power n equals to 1 plus n x. So this is what I'm going to use here. So if we are using that case here, so this will be g m e by r e square, and then we will have 1 plus this thing multiplied with this n. So minus 2 into h by r e, and ultimately we will have g equals to here g m e by r e square, and 1 minus 2h divided by r e. This is what we can get. So at any distance. And what about h is 0, means on the earth's surface? So in that case, okay, let me do one thing here. Notations should not be colliding with each other. So I am replacing, in this particular case, I am writing g outside. For g outside, I am using here g out. So here g out. Okay. So everywhere we are taking this thing g outside, and then we will have here g outside. Soon you will understand why I have written here g outside. So here we have acceleration due to gravity, and in the case where a body is placed at a height of h from the surface of the earth, this is what acceleration due to gravity. Now what if h is 0, that is the body is at the surface or on the surface of the earth. So in that case, if h is 0, I'm writing here second case, on the surface. So in this case, the only distance between these two things, means the center of the earth and the body, will be the radius only, and h equals to 0 on the surface, that is h equals to 0. And in this case, g will be, let's say on the surface I'm writing only g. So this h will be 0. So this will be 0, and then we will have g me by re square. So in this case, g will be only capital G mass of the earth me by re square. And if you put all these values, you will get nearly 9.8 meter per squared second, and it is different at poles and at equator. So from equator, if you are moving from equator to pole, its value will increase. So from equator to pole, this g will be increasing. Now we have a standard acceleration due to gravity of a body which is on the earth's surface itself. Okay. And if it is at height h, we will have this one. So g at a height of h can be written as, let's say, g out. This can be written as, look, g me by re square. This is, we have taken acceleration due to gravity on the surface, and then 1 minus 2h by re. This is acceleration due to gravity at height of h. Now coming to the next point, we have obtained at the surface what is the equation for acceleration due to gravity when the body is on the surface, and mostly we using this thing for the bodies which are near to the surface, means where h is much less than this re. Okay, now coming to the case where a body is placed inside the surface. So in this case, let's say I'm bringing it a little bit down. So in this case, when a body is inside the surface. So third. Okay. So this is center of the earth. And let's say a body is placed here. Here, it has mass small m, and its distance from the this straight line. This is, let's say, r prime. Let's say its depth is d, means it is at a depth of d from the surface. So from here to here, its depth is d. Now, we have already discussed such a problem where we have found out what is the gravitational pull on this body at this point. So I'm going to take that reference here. Gravitational pull at this body, and mass of this earth is me, and radius is, let's say this is radius, and this will be re. So if it is inside the solid sphere, and we are assuming that this solid sphere is uh, uniform, so in that case we can check this thing. Look, starting from here, I have just described inside, and then we can continue in this way, and ultimately we will reach that force, gravitational force on this body at this point will be this much. Now I'm going to replace this thing here. So in this particular case, Fg will be, I'm writing Fg only. Okay, this is the force. Fg will be G me divided by re cube, and mass of this body, there it was m prime, and then we will have one more thing here, and let's check what is that. So this is r prime. So this will be the distance r prime. Okay. So I'm writing this thing here. This will be r prime. Now this r prime, if we are trying to write in terms of radius of the earth and its depth from the surface, so this r prime will be re minus d. So we can write g me into m. Here I have taken m instead of m prime, and re cube into re minus d. And then we can write what is the acceleration due to gravity here. Let's say g inside. So this will be g me divided by r cube, because fg divided by m will give us g me by re cube into re minus d. And then we can rearrange the terms to make it little bit convincing. So this will be re square into re minus d and divided by re. So this is what. Now, I guess you have figured out this thing. What is this? This is acceleration due to gravity on the surface. So we have using g here, and then this will be 1 minus, look, d by re. So if there is a body placed inside the earth and its distance from the surface of the earth is d, then acceleration at that point will be acceleration due to gravity on the surface multiplied with this term. Okay, this is all for this video. In the next video, we will continue our discussion.